let's look at another interpretation of what we've been talking about. Let's say you have a cross-section of a landscape. Maybe it's a nice national park. Maybe it's a coal mining region. And all these mountains and valleys are just too much of a pain for you. So you are going to bring in the world's best drawing of a bulldozer. Like that. And you are going to shave off the mountaintops and use them to fill in the valleys, make a nice level road. So I guess we'd get something kind of like that. So the question is, what level will that road be once you're done shaving off the mountaintops? I mentioned coal mining. There's something called mountaintop removal mining, where instead of digging into the earth and pulling out the coal, you just push all the stuff that's on top of the coal off the top of the mountain into the nearby valley. Does that sound like a good idea? It's up to you to think. So what level will that be once it's all level? So think about that for a second. So we're asking what constant y value, constant meaning level y value, would give the same total area under the curve, right? Because we're using this area to fill in that area. At least from A to B. What constant y value would that be? Does it make sense that that would be the average value of the function? So if we draw another function here, and let's say I'm starting here and ending here, I'm asking, consider that total area. What rectangle with a flat top has the same total area from A to B? That would probably be somewhere like there. You can see this part probably isn't enough to fill in that. You would need some of this to help fill that in too. That's another interpretation of the average value. Now you might have noticed that the average value intersects the curve here, and up here what I kind of drew also intersects the curve. So there's a theorem that says that will always happen, so let's talk about that. It's called the mean value theorem for integrals. Back in Calc 1, there was a mean value theorem that was for derivatives. Is there a relationship between the two? Well, I'll let you think about that. But try to take what we just said about there being an intersection between the level version and the actual curve itself. Try to formulate that mathematically before I write it out, and then maybe I won't even get it right. So we'll see. Okay, welcome back from trying that. So can we say there's at least one horizontal position because we saw in some of the others there was at least one, there were two, maybe even more. So at least one horizontal position, and we're going to call that C, in the range we're talking about, or the domain we're talking about, where the function at that horizontal position is equal to the average value of the function on that interval. Which you could write as 1 over b minus a integral a to b f of x dx. Does that sound like a reasonable way to say that the level curve, or the level version, after you've shaved off the mountains and filled in the valleys, will intersect the original landscape function at least one place in the domain that you're talking about. Is this a good overall definition? Can you think of a counterexample to this? Maybe a function that's not so nice? And how can we use that to modify this definition? Well, let's leave some space here, and we'll draw maybe a curve that we've already done. We had A and B, and we had something like that. That seemed to work. But what about another situation where we had like f of x was 3 for a while, and then it was 11. What's the average value there? It was something like that. But that doesn't intersect our function, does it? So that function doesn't work for this mean value theorem. So this doesn't have a c like what we just said there. So what can we say has to be true for the function? What's an example of what's true for this function but not for this function, that let this function get away without going through that value? Well, this one's continuous and that one's not, and that turns out to be the same, the big deal. So we can say as long as f is continuous, on A to B. So that's why we left that blank line there. So that's the mean value theorem. Sometimes people write it a different way. They just multiply both sides by b minus a. So they might say f of c times b minus a is equal to the integral a to b f of x dx. Either way is good. This way doesn't really scream out to you average value of the integral because it doesn't have that 1 over b minus a there. But if you see something like this, you can translate it to that if you want to think about average values. Let's talk about finding the c value. Let's use an example we had before. We had x squared from 0 to 1. And we learned that the average value was equal to 1/3. So what c value will give you an x squared value of 1/3? So we would just write that we're going to solve x squared equals 1/3. Just take the square root on both sides, you get x equals root 1/3. Pretty nice algebra, right? What if the algebra isn't so nice? Anytime you take a square root, you should think about should the answer be plus or minus, but here we're only operating on positive territory, so I would only need the plus version of the square root. What you can do is in Desmos, you could say f of x equals x squared, and then also say y equals 1/3, and it will plot a horizontal line. So it'll give you a drawing like this. And if you click on one of these curves, it doesn't have a curve or line, click on one of them, it will show a gray dot where they intersect. And then just hover your mouse near that and it will report to you the x and y value. It doesn't give it to you with an infinite number of decimal places, but at least it's like 3 decimal places, which is good enough for the kind of stuff we're doing. So we'll say hover the mouse near that. and it'll show the x and the y. Now, Desmos isn't the most professional tool. What if you wanted to do this in Excel? There's something called goal seek, and you can find videos for that online, but I just wanted to mention the more useful skill in the future.